This video here is a bit of an introduction to Coulomb's law. What Coulomb's law tells us in electricity is what actual force exists between two charges. So now I've written Coulomb's law up here, so you can see all the salient terms here. It's a force, and it is a vector, meaning it has a direction and a magnitude. There's a constant here, K, and it calls for a Q1 and a Q2, and an R, which is the distance between two charges. So again, what we're talking about here is if we have two charges like this, say here's a positive charge right here, and here's a negative charge right here. Sort of empirically, as we've discussed in different videos, we know these charges will attract each other because they're opposite. But exactly how strong is that attraction? Well, that's what Coulomb's law tells us. So what we have to look at then is we have to say, well, here's some charge here. Exactly how much charge do we have in this positive case here? That would be Q1. And exactly how much charge do we have in this negative case here? That would be Q2. Or you could reverse them. It doesn't matter. The point is that Coulomb's law just calls for the amount that both charges have here. And the thing that also calls for is it matters how far the charges are apart. This is the distance r between the charges right here. So if they're 1 meter apart or 1 millimeter apart, the force will vary because there's this r squared here in the bottom of Coulomb's law. So that all matters there. K is just a constant here. The value of K is 9 times 10 to the 9th. It's very easy to remember. This has those two 9s in there. And the units of it are a bit of an alphabet soup here, but it's a Newton meter squared per Coulomb squared. Those are sort of the units of it right here. And so if you ever wanted to calculate, well, what is the force between two charges here, you would just plug into this particular equation. Here's the force constant here, the amount of charge here, the amount of charge here, and the distance between them, and you'll get your force. There's a few things you have to be careful of when you use Coulomb's law, and I'd like to make a few suggestions here to help you be successful with your use for it. Okay, the first thing that you have to be concerned about is what actually does r hat actually mean? What does it mean to have a vector with a little hat over it? Well, what it means, of course, is that, unfortunately, charges are not always going to be oriented nice and neatly along, say, an XY coordinate system like this. Like if the charges were here, say there's a positive charge right here and there's a negative charge right here, if we wanted to know what the force is between these two charges, we'd say something like, well, this negative charge is going to be attracted to the positive charge along the negative x-axis. This arrow is pointing to the left, so that would be the negative x-axis. That would be very easy to classify. Or if there was a negative charge right here at the origin and there was a positive charge up here, we could say that this positive charge is attracted downwards towards the negative charge like that, and its direction would be along the negative y-axis. This is the x-axis, this is the y-axis. That would be fine too. But the problem with these charge pairs or any system of charges is they don't always have to be aligned along the xy axis nice and neat like that. Like, for instance, in the case I've drawn just up here, here's a positive charge right here, and here's a negative charge down here. So if we want to know what force this positive charge is feeling, it's sort of down this way, isn't it? Because it's going to be attracted towards the negative charge. Like if you wanted to superimpose an xy coordinate system on it like this, here's that positive charge right here. This force, F right here, is neither along the x or y axis. And you can have all kinds of orientations like this. You can have charges like here's a negative and here's a negative. Or here's another Cartesian coordinate system. Here's a positive down here. Here's a positive over here. The force is always along that direct line that connects the charges, but these things are never along the x or y axis nice and neat like that. So it's very hard to classify the direction. But that's exactly what this r hat vector is for. So whatever that direction is like that, so if you have a positive charge here and a negative charge down here, this is the force right here. This positive charge will be attracted that way towards the negative charge, and we just empirically call this direction here r hat. That's the direction between them. Or if there's a positive charge over here and a positive charge over here, well, the force on this positive charge is going to be up and away that way like that, and that's again along the line that connects them, but we would call this direction here the r hat direction. So we sort of reserve r hat here as sort of a direction reference for Coulomb's law. It's an awkward thing, but it really just has to do with the fact that these charges will not always line up along a nice, neat XY axis the way it would be if it was nice and convenient. They just don't work like that. And so in some cases, you might actually have to drill down and figure out what r hat would be, but of course you can use your sines and cosines and so on to figure that out. Lastly, then, I want to just reference something about the direction, being a bit careful about these things here. So suppose you have a positive charge right here, and you're going to have a negative charge right here. And I'll just put them on a line like that to make it sort of simple for us like that. When you go to use Coulomb's law then, here's Coulomb's law here. Of course, F is the constant K times Q1 times Q2 over R squared. And suppose this positive charge here has something like, let's say, 10 nanocoulombs of charge, and this negative right here is like minus 5 nanocoulombs. So it doesn't have to be an individual proton or electron, but they've actually been charged so highly that they're into the nanocoulombs now. Remember that nano is 10 to the minus 9 coulombs for your calculations. Let's just see what Coulomb's law would predict. So if I sort of plug these numbers in here to the force law, I'll get the K here, and at some point I could put in the 9 times 10 to the 9th. I'm going to leave it out for now. But the positive here would be 10 times 10 to the minus 10 coulombs. The negative right here would be minus 5 times 10 to the 9 coulombs, something like that. And of course you need the distance between them squared here. Let's just say they're down here, and I'll just say the two charges are maybe 1 meter apart. So there'll be a 1 squared in the bottom. Okay, so we won't bother calculating it right now, but what I wanted to point out then was that because this K is a positive number and what you square in the bottom is always a positive number, this is ultimately there's a multiplication of a positive number times a negative number right here. So this is overall going to generate a negative number. So if you calculate all this out, you get that the force is a negative some number, and it will be in newtons if you've done everything in meters and coulombs and things, but you'll get a negative number. So the question is, what does this negative really mean in front of the force right here? It does have to do with the direction, but which are we talking about here? Because we know that, say, the positive charge is going to get pulled this way with this amount of force, and the negative charge is going to get pulled that way with that amount of force. So what does the minus sign actually mean? Some of you may think that it means direction, and we might be comfortable a little bit with this because if I draw a Cartesian coordinate system like this, we know that this is the positive x direction, and that's the negative x direction. That's just the way the Cartesian coordinate system works. And so the negative sign might mean the force is to the left because that's the negative direction. And that's partly right because the electron is getting pulled to the left, so maybe that's correct. But then how do you reconcile this negative sign for the proton right here, which is actually, or the positive charge, which is going towards the right? That's the positive direction. See, it gets a little bit confusing in there. So what I'd recommend doing whenever you use Coulomb's law is to always use Coulomb's law form of it like this. Let me just pop up here a bit and maybe write a slight correction up here. I'd always recommend never putting in the charge values directly, but always putting their absolute values here. So I would always use a version of Coulomb's law that looks like this. I'd put a K here, and I'd always be sure to put an absolute value sign around all of my charges before doing any computation with it like that. This is an R squared, and this is an R hat. I'd always recommend doing that to always make sure that the force here is always going to come out to be a nice positive number. The absolute value sign will always guarantee that because K is a positive number. When you square a number for the distance, that will always be positive, and this absolute value here will guarantee that whether you have positive or negative charges here, your result will always be a nice positive number. How would that help us? Well, if we did that down here, that means we would have an absolute value sign here, 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 and here. And instead of getting a negative number right here, we'd get a nice positive number for the force. Now, what does that mean? Well, now it means we have to use a bit of our common sense now to start assigning these directions. We're not going to leave it up to a mathematical sign to dictate what's going to happen here. So what we do is we're going to get some number here for the force. And I don't know what the number is, but it's just some number here. And our common sense now for the directions will tell us to do the following here. We'll say, yeah, our common sense tells us that opposites attract. So what that means is, yes, the positive charge will be pulled towards the right with this amount of force. But that's our conclusion. So we could write over here, F is just some number. Remember, this number is always a nice positive one right here. So we're just going to say that the positive charge gets attracted to the right with this amount of force. End of story. What do we do about the negative charge? Well, they're like charges. They have the same force between them. This force on the negative charge will also be that same number. It'll be some number right here, but it's to the left. But the sign isn't going to dictate that to us. Our common sense is going to. So we sort of conclude this problem here. Is the positive charge, let's just say, to the right with so many newtons, some number of newtons. The negative charge here is going to be to the left. Again, these are the ultimate force on to the left with some number of newtons. We assign the left and right in the direction ourselves. We don't rely on the minus sign to do that for us. So be careful if you use Coulomb's law. I strongly recommend always putting the absolute value and always getting a positive number for the force, and then using your common sense to assign the ultimate direction. So I'd like to look at just one more case of that.